Hello students, today we are going to study angular simple harmonic motion. The name itself suggests or explains that the vibratory motion is along the arc of a circle. For example, we take here a rod suspended by a string from a rigid support. This is the equilibrium position of rod. If it is displaced from its mean position through angular displacement theta and released from this position, say A dash, then it comes to O and then to a new position, say for the rod the new position can be shown by B dash here. So the vibrations are along the arc of a circle. Here continuous vibratory motion is there and these vibrations are called angular vibrations or angular oscillations. Also, those oscillations are called torsional oscillations. In this case, the angular displacement is given from O to A, but torque acts on it towards the mean position in both the cases. Here we can write tau is directly proportional to theta and having opposite direction. Similar is the example we take here for a metallic disc. Here the disc can be shown like this. It is metallic disc suspended by means of a thin wire from a rigid support. If the disc is slightly twisted in, say, anti-clockwise sense here, then released from it, then also this disc performs the rotational motion. But here the rotational motion is partly clockwise and anti-clockwise sense. So try to understand this motion. The motion is not along the complete circular path but on the arc of a circle. It is partly clockwise and anti-clockwise sense. Here also the angle of twist or angular displacement is denoted by tau. The torque acting on it, angular displacement is denoted by theta here, and the torque is tau. Tau is directly proportional to theta and both are having opposite direction. Tau is directed opposite to theta. Let us observe oscillations of a disc. In the experimental setup, a metallic disc is suspended by means of a thin wire from a rigid support. If the disc is twisted about the axis along the wire and then released, then it performs rotational motion, which is partly in clockwise and anti-clockwise sense. Such oscillations are called angular oscillations. You have observed the angular oscillations in case of a metal disc. Now, for this metal disc or rod vibrating along the circular path or arc of a circle. Here we have taken that tau is directly proportional to theta and having opposite direction to that of the theta. Combining these two, we can write tau is equal to minus theta, and tau can be written as minus c theta, where c is constant of proportionality. It is also called as twist constant. Now, when we have such examples of oscillatory motion, the body which performs angular oscillations, it possesses moment of inertia. If it is denoted by I, is the moment of inertia of body. For during the oscillations, alpha is angular acceleration. Then we can write the torque necessary for the rotational motion is tau is equal to I alpha. Suppose this equation we write as equation number 2. We can, from equation 1 and 2, we write I alpha is equal to minus c theta. Means alpha can be equal to minus c upon I into theta. This is equation number 3. So when we observe equation 1, tau is directly proportional to theta and has opposite direction. From the equation 3, we conclude that angular acceleration is directly proportional to angular displacement and having opposite direction. So from these two relations, we can define angular S.H.M. I have already written here that angular S.H.M is defined as oscillatory motion in which torque or angular acceleration is directly proportional to angular displacement and its direction is opposite to that of the angular displacement. This concept is similar to linear S.H.M. In linear S.H.M, we have taken the expression as F is equal to minus kx. Here tau is analogous to force, theta angular displacement is analogous to linear displacement, and here c, which is the twist constant, it is analogous to k, which is force constant. Now here the new quantity we have the c, constant of proportionality, which is the twist constant. Here we write for the twist constant like this: tau is equal to minus c theta. We consider c can be written as minus tau upon theta. If we write its magnitude in this way, c is equal to tau theta by magnitude. So here this new quantity, twist constant or c, can be defined as restoring torque per unit twist. So this is another definition here. This c is defined as restoring torque per unit angular displacement. The simple definition here for the twist constant, like our force constant, constant k is equal to, by magnitude it is F upon x, that is force per unit displacement. Here it is restoring torque per unit angular displacement. Restoring torque is having unit Newton meter and theta in SI unit express having unit radian. So for the twist constant, the SI unit is Newton meter per radian. So this is about the new quantity and some expressions which are related to angular S.H.M, definition of angular S.H.M. Now we turn to the next sub point, which is differential equation of angular S.H.M. So here we try to derive the relation is differential equation of angular S.H.M. This is also very simple. We have already three equations. Tau is equal to minus c theta, tau is equal to I alpha we have taken. From this step we start the derivation of differential equation. We use all these three steps which we have used for definition. Tau is equal to I alpha, equation 2. We have obtained alpha is equal to minus c upon I into theta. Now alpha is the angular acceleration. It can be defined as rate of change of angular velocity with respect to time, d omega by dt, derivative of omega with respect to t. We can take d dt of omega, we can substitute as d theta by dt, which is the rate of change of angular displacement. So we get here the final relation for alpha, which is the double derivative of theta. Alpha is d square theta by dt square. If we substitute it in equation 3, we get, substituting in equation 3, we get the state like this: d square theta by dt square is equal to minus c upon I into theta. This is equation number 4. Adjusting it, d square theta by dt square plus c upon I into theta is equal to 0. This is equation number 5. And it is called as differential equation of angular S.H.M. So like the differential equation in linear S.H.M, we have written it like this: d square x by dt square plus k upon m into x is equal to 0. This is the differential equation for linear S.H.M. Similar or analogous relation we have derived here. X is replaced by theta, k is by c, and m is replaced by moment of inertia. We know in rotational dynamics we have shown that I is the moment of inertia, which is analogous to mass in translational motion. So this relation, equation 5, which is differential equation of angular S.H.M, is analogous to differential equation of linear S.H.M. So this is about the differential equation. So there is one question: obtain differential equation of angular S.H.M. So we have to start from this step. According to definition of angular S.H.M, tau is directly proportional to minus theta, means it is directly proportional to angular displacement and having opposite direction. Here it can be written as tau is equal to minus c theta. C is a twist constant. It can be defined as torque per unit angular displacement. If we take I alpha, which is the familiar equation, tau is equal to I alpha, equating the right hand sides of both the equations, we get here alpha is equal to minus c upon I into theta. alpha can be substituted as double derivative, and then we have obtained equation number 5. Now we have to study here one example of Angular S.H.M. That example is of a magnet vibrating in uniform magnetic field. So this example we have to study and obtain the relations for the vibratory motion. For that, we consider the system in which there is a magnetic field which is directed, say, from our left to right, and its strength is denoted by B. It is also called as magnetic field strength or magnetic induction. This magnetic induction is uniform, in which there is a bar magnet placed like this with its axis remains parallel. North pole of the magnet, south pole of the magnet. Here the magnet can be shown here by red line. I can show here is so it can be shown here by the here N and S denotes the magnetic poles of the magnet, and this is the axis of magnet. This is the equilibrium position of magnet, because magnet remains along the direction equilibrium position of magnet. Magnet remains parallel to the direction of magnetic field, and north pole, south poles are adjusted like this. Here again we have to consider the same magnetic field. Uniform magnetic field. And the magnet is slightly deflected from its position. Here original position is like this. This is the axis. From this original position, the axis is shown in this way. This is the angular displacement. Magnet is deflected, or it is taken through angle theta and then released. Then it performs angular acceleration, angular oscillations. In this way, I can show with pen like this: original position, new position, and then it performs the angular oscillations. Here north pole, south pole can be shown. Torque acts on the magnet. That torque is given by the vector equation mu cross B, where mu is magnetic dipole moment of magnet. So in this case, tau can be equal to mu B sin theta by magnitude. Its magnitude is mu B sin theta, but if we take the relation, it is minus mu b sin theta. This is our first equation here. Torque acting on the bar magnet is minus mu b sin theta, because here theta and tau are having opposite directions. If we take theta as small, as theta is small, we consider sin theta approximately equal to theta. We can write tau is equal to minus mu b theta. This is our second equation. Now, as the magnet is vibrating, it has the angular acceleration. We take here, let I is moment of inertia of bar magnet or magnet, alpha is angular acceleration. Then we can write tau is equal to I alpha. So this is equation 3. Now, equating RHS. Here LHS are same, therefore RHS can be written as I alpha is equal to minus mu b theta. Alpha is equal to minus mu b upon I multiplied by theta. This is equation number 4. Here mu, that is magnetic dipole moment of magnet, is constant. B is uniform magnetic field is constant. I moment of inertia is constant. Therefore alpha is directly proportional to theta. We write angular acceleration is directly proportional to angular displacement. Here we can write negative sign, angular displacement with negative sign, so that we say that here angular acceleration and angular displacement are having opposite direction, and this is the condition for Angular S.H.M. So we say that here motion of magnet, motion means oscillatory motion or vibratory motion. Here we write it clearly, oscillatory motion of magnet is angular S.H.M. Why angular S.H.M? Because we have proved that alpha is directly proportional to minus theta. Or in words we say that angular acceleration is directly proportional to angular displacement and having opposite direction to that of the angular displacement. So the motion is definitely angular S.H.M. Now the next step in this angular S.H.M is that we have to find the period of magnet. As there is vibratory motion, it has a period or periodic time. Periodic time can be written here as a point. Period, it is denoted by T, and T can be equal to mathematically twice pi upon omega. It is in words we can write twice pi upon inside the square root. It is angular acceleration per unit angular displacement. So here we can substitute twice pi upon under root. So what can we have here? Angular displacement, angular acceleration upon angular displacement. So from this relation, from equation 4, alpha upon theta is equal to minus mu b upon I. And if we consider the magnitude, we write it as mu b upon I. So here alpha upon theta is the angular acceleration per unit angular displacement. Here alpha upon theta, and t is equal to twice pi under root mu b upon I. It can be t is equal to twice pi under root I upon mu b. So this is the expression for period of a magnet. We can give the number for this as 5, and this last equation, this is we considered it is equation 6, and last expression as 7. Period of a vibrating bar magnet when it is placed in the uniform magnetic field of induction B is twice pi under root I upon mu b. Now here, while deriving this period, we have taken the basic I alpha is equal to minus mu b theta. This minus mu b theta we have obtained from this relation tau is equal to mu cross b. So this relation we have taken from the portion of magnetism in the 11th standard. It is assumed that here we have to consider this expression. Actually, direct equation or derivation is not there, but we have to consider by considering the analogy of electric dipole moment. So this is expression we have taken here. But in the 11th chapter, magnetic materials, we have to study that equation in detail. But for this stage, this derivation of tau is equal to mu cross b is not expected. But for the understanding, I can explain the derivation here, which is the side derivation or side calculation. It can be like this. We take the simple derivation here so that you can write it and understand it. So here, in the displaced position of the bar magnet, when north pole is shown by letter N, here letter N, on this pole of a magnet, the force acts on it. That force is denoted by Qm into B. So I take here only the derivation of this mu cross B. So force acting on north pole is Qm into B. And on the south pole, the force acting is minus Qm into B. The distance between two forces, this perpendicular distance between two forces is denoted by Np. And here the angle between Sp and this Ns is equal to theta. We can write tau or torque is equal to force multiplied by perpendicular distance. Perpendicular distance between two forces. Between two forces means QMB and minus QMB. So one force is QMB by magnitude and perpendicular distance is NP. From figure, NP is equal to NS sin theta. NS, this distance, NS. Usually this distance in case of bar magnet, you know it is denoted by twice L, always. So QM into B, NS is twice L and sin theta. Here we write QM into twice L separately and B sin theta. So QM into twice L is denoted by mu, and mu is called as magnetic dipole moment of the bar magnet. It is equal to product of pole strength and magnetic length twice L. So it is mu and into B sin theta. We know that mu is a vector quantity. It is having direction from S pole to N pole. So in a magnet, if there is south pole and north pole, mu is having direction from south pole to north pole. So here mu is vector, B is vector, therefore we can write vector product of mu and B. So this is torque in vector form. So this is simple derivation of a torque acting on a magnet when it is placed in uniform magnetic field. So just I revise here. In the displaced position of the bar magnet, force act on each pole. Pole strength is QM. QMB is the force acting on north pole, minus QMB is the force acting on south pole. Both are separated by perpendicular distance NP. They constitute a couple. That couple can be expressed in terms of a quantity torque. It is defined as force, product of force and perpendicular distance between two forces, QMB into NP. NP is the perpendicular distance, and the mathematical steps, you know, NP can be NS sin theta. Adjusting QM into L in separate bracket, we have definition of magnetic dipole moment. Then it is denoted by mu B sin theta. Mu is a vector quantity and this vector tau is equal to mu cross B. In our derivation, we have taken it directly. This explanation is not important in this theory of angular S.H.M. We have to take directly tau is equal to mu cross B. But for the sake of understanding, we have taken this derivation. We have to repeat it in the chapter number 11. But for this stage, you can note down these steps in side notes or in your notes in any corner. So this is about angular S.H.M. We have proved in angular S.H.M. we have defined angular S.H.M. We have taken examples of angular S.H.M. and in detail we have considered the motion of magnet in a uniform magnetic field. Its motion is angular S.H.M. We have derived the expression for period also. So today we stop here. Thank you.